Okay. Hi, everybody. So today we have kind of not really a lot of new information, but we do have some sort of applications and some types of things that you can do with exponentials. I think that it's important to take a whole day to just talk about what are the real world things that we can do here, because it's important to understand that this is really one of the most real world things that we do in this class this year. Just for your reference, we're working on learning targets 7A and 7C. Really, we're focused on the real world applications of things and looking at graphs and figuring out what they do. The word logarithmic is in here, but that's not until, we're not going to really use that until next lesson. This list is probably a lot longer than I have it, but here are sort of some of the things that you can do with exponential growth. We've seen some of them already, but just for your reference, this is sort of a good list. You can model population growth and decay just by kind of looking at how many people or animals or bacteria or whatever there are in an area and watch them grow. And that happens exponentially typically. Virus spread is a really good example, and it's relevant right now because of coronavirus, but it does tend to happen exponentially until mitigation strategies are put into place, like social distancing. Radioactive decay is something that you might have seen a little bit of earlier this unit, but also it is an exponential decay example. So that's a really good use of exponential decay. Compound interest we've talked about. Stocks we have not seen yet, but it's kind of interesting because sometimes stocks grow exponentially. And then inflation is another good example of something that happens exponentially sometimes. We're not going to dig into every single one of these today because some of them are a little bit messier to investigate, but I just wanted to say, you know what, like they do exist and they do happen in the real world. Hopefully you have seen a graph that looks a lot like this before. But what I want to do is I just wanted to highlight the spots where we have some exponential growth. Right at the very beginning of COVID, there was some little exponential growth there. There's a little exponential growth happening right here. There's a little exponential growth happening here. There's definitely some here and definitely some here. Those decays, the spots where the graph is going down, it's a little bit harder to tell, but it probably still is a little bit exponential. So you might be able to say, okay, well, there's a little exponential curve here and a little one here and a little one here and here and maybe even here. It's hard to tell what's going on there. This is from the New York Times. The next example, which is a little bit less familiar to me, but maybe you've seen this in biology. This is mitosis, which is one of the processes of cell reproduction. And what happens is one cell turns into two cells, and then two cells turns into four cells, 2, 3, 4. And here we can kind of model this by saying, well, each reproduction cycle, which is like an x, we go 2 to the x. And so, for example, this is like step 0. This is step 1. This is step 2. And so if you put those step numbers in, this is almost like a geometric sequence. You can see, okay, well, we're going to have 2 to the 0, which is 1, 2 to the 1, which is 2, and then 2 to the 2, which is 4. And so now we could say, well, how many cells are there going to be in step 48? So then you do 2 to the 48. Which would be a big number. It's probably scientific at this point. Yeah, it says 2.814 times 10 to the 14. So that's a really big number. But it's kind of cool that you can use exponential growth to talk about, okay, well, how many cells are there going to be generated at each step? The next example, and I'm not going to do much analysis here, but because this is sort of a current event, I guess it's not super current, it happened like a couple weeks ago, but the way that GameStop stock exploded like really quickly over kind of a couple of days, you can see that this is a pretty exponential curve here, right there. And so normally we'd say, okay, well, this is going to keep growing, but then there were those corrections where like some stuff happened with the market where they were like, well, you can't keep trading that. So that's why it kind of started to go back down. So yeah, that's all I have to say here. But really, what's important is that sometimes these types of things grow exponentially. What I guess I was getting at on the last slide there is that despite the trend of exponential growth in places, and we talked about this graph already, but despite that growth, there's often a turn around. So things start leveling off eventually. Start leveling off here, starts leveling off here, starts leveling off and leveling off. And what I mean by that is, well, in the world, exponential growth often has limits. And so because of that, you can't really say it's always going to be an exponential growth function. But for parts of things, like if I was guessing what was happening right in here or right in here, I might be able to use an exponential function to model this. Obviously, this is that coronavirus example. And so when we think about, well, what happened here, or what happened here, or what happened here, those are the spots where the mitigation strategies starts working. And so if you think way back to the beginning of like March and April of last year, Governor Walz or whoever else was talking about flattening the curve. And so flattening the curve refers to, let's take an exponential growth thing and start slowing it down. So now it's not as exponential anymore. And so we can use that sort of idea about like, okay, well, when is the curve flattening? When is it becoming either linear, or when is it becoming maybe flat, or maybe it's decreasing or something like that? Those are the types of questions that we can ask, and it's cool because we can start using exponentials, but then some other types of functions become more valuable at other times. That's a whole lot to say that exponentials are useful sometimes and then also sometimes not useful. There are two important kinds of questions that we're going to start being able to answer, I think maybe either next lesson or the lesson after that, about exponential graphs and functions and models. And one of the important ones is, how long is it going to take for an exponential model to reach a certain value? So like if I want to know, okay, well, I have this coronavirus curve and it looks exponential, how long is it going to take if we take no precautions? How long is it going to take until it gets to this spot? That's an important question, because then we can start making some plans about what types of mitigation strategies might we need to respond to that type of growth, etc. We don't have the tools to do that right now, but we will get those tools in the future. The other one that is really important, and this is especially important for continuous growth, especially, which means we're using A equals PE to the RT. Finding this growth rate right here can be very difficult because it's in the exponent. And the same thing with the time. If we're working with A equals PE to the RT here, then we're working for trying to find the time. And those two things being in the exponent are just difficult to get, and we don't have the tools to do that right now. Two things that we do have the tools to do, though, are to find A and P. Okay, so this is in A equals PE to the RT. Finding the amount you have after a certain amount of time, if we know R and T and we know P, then it's easy for us to find A. We've done a lot of that. We've just put in numbers for T and seen what we got out. That's what I mean when I say find A. The other one is finding P, because P is also something that we can just determine. If we know R and T and A, then we can solve for P. This is sort of a little summary slide, so you can pause this video right here and read this. All it says is just what I just said. We don't have the skills to solve for R or T in this equation, A equals PE to the RT, but we do have the skills to solve for A or P, depending on what information we have. Okay, so let's take a look at doing some examples like this. Here is a piece of information about a bacteria. A bacteria is a type of I'm not even going to pretend that I can explain what a bacteria is, but it's something that grows exponentially, and we know that bacteria can often lead to illness, especially if it's in a food. And so one example of a bacteria that shows up in food is E. coli. You can get really sick from having E. coli. E. coli in an ideal environment in a lab, which just means we're trying to make it grow as fast as we possibly can. E. coli grows at a rate of 207.94% per hour. Okay, so that sounds like an R. If we turn the percent into an R, we write 2.0794. This is our rate every hour. We have a scientist who is starting with 12 bacteria cells, so she's putting that set of 12 bacteria cells into a petri dish or something like that. She is trying to figure out how much she will have in 40 minutes, so or 2 hours afterwards. Okay, so this is a continuous growth because it says the word continuously, and so we're going to use A equals PE to the RT. We know an R, and we know our T, or we know our P, sorry. We also are given what we're going to put in for T. So we're going to put in 40 here, and then we're going to put in 2. Although this says 40 minutes, our rate is written in hours. 40 minutes is 40 minutes out of 60 minutes in an hour, which is 2/3. So you're going to use 2/3 as your T here, not 40. If you put in 40 there, that would mean 40 hours in this context. Okay, so A equals 12 E to the 2.074 T. And you're going to put in this 2/3 here. It's good to use your calculator for this, and one reminder about using Desmos is just remember to have parentheses right there so that this T doesn't jump down to the out of the exponent, which happens sometimes on Desmos. Okay, 12E to the, 2.074, and then times 2/3. And your answer here is you get 47.826 cells. It's hard to say what that decimal means, but we'll keep it for our purposes. Okay, in 2 hours, you change the 2/3 to just 2. And then you say, okay, well, in 2 hours, you'll have 759.69 cells. Okay. This scientist was forgetful, and he forgot to figure out how many cells he started with. So we have an amount that we have now, and we have a number of minutes, or a number of hours. So we have A is 1536. We have T equals 3, and then we're going to keep that R, 2.074. Okay, so now we have to solve for P. So we have 1536 equals P E to the 2.074 times 3. Okay, so you can do the 2.074 times 3, and you get 503.71. We'll say 71 P. All of this is what this is when I put that in my calculator. Okay, equals 1536. So then when we divide by 503, we get 1536 divided by 503.71. Let's be precise here, Mr. Nelson. Okay, and we get 3.04. So P is what P is. So 3.049. So this is about 3 cells is what they started with. Okay, so that's one example of what we can do with exponential growth in a biology context with showing exponential growth with bacteria. One sort of straight up algebra type of problem is how can we figure out what an equation that looks like y equals ab to the x given two data points on the graph. And so this is a little bit of a challenge because we aren't super familiar with this, but really what we're going to do is we're going to set up a system of equations to solve this problem, to figure out what A and B are. Notice, if you would, at the very beginning here, the asymptote is still y equals 0. And we're going to assume that we're not having any horizontal translations either. So our answer will be looking like y equals ab to the x. So we have y equals ab to the x, but we have some values that are given to us. We're given an x and y value, so we can write an equation that says 75 equals ab to the 2. And then we can also say, well, 375 equals ab cubed. So I'm taking these points, x and y, and putting those values in for x and y in the equation. Now our job is to figure out what a and b are. So this is really a system of equations with two variables in it. The two variables that I need to know are what a and b are. So how can I do this? Let's take this first equation and figure out something we can do with it. So 75 equals ab squared. This is a little bit weird. Let's divide both sides by b squared. Because I'm thinking, okay, if I do that, then I'm going to get a on its own over here. A is 75 over b squared. And then what you can do is you can take a substitution and you can put this into the other equation where you see it. So now we have 375 equals 75 over b squared times b cubed. Well, check this out. This is an exponential. You have exponents multiplied together. Actually, it's really divided, right? These are kind of like that. And so now I know that that's going to be a b to the 1 from my exponent properties from last unit. Well, b to the 1 is just b, okay? So then we can solve for b in this equation just by dividing by 75. Okay, well, b then is 5 because 375 divided by 75 is 5. So now we know b, so let's figure out what a is. Let's take b and put it back in up here. 75 equals a, and now we know b is 5 squared. Okay, well, 5 squared is 25, so now we have 25a equals 75. And then if we divide both sides by 25, I get a equals 3. So the equation that matches this graph is y equals 3 times 5 to the x. This is a super similar problem, so I want you to start doing that one, and then I'll go back through it afterwards. So here we go. All right. We know we want y equals a b to the x. That's what our answer should look like. We just have to figure out what a and b are. So we're going to put in 0, 40, ab to the 0, okay? And then we're going to put in 120 equals ab to the negative 1. Okay, so here's the cool thing about this one. If you take a look at this equation right here, well, b to the 0 is 1 because anything to the 0 is 1. And so what we have is 40 equals a already. So now we know a is 40. So then put it in here. Well, 120 equals 40, b to the negative 1. Okay. Remember your exponent properties. This b to the negative 1 means now I can rewrite that as 120 equals 40 over b. Okay. So then let's multiply both sides by b, and we get 120b equals 40. Divide both sides by 120, and we get b equals 1/3. Okay, so our equation that matches this graph is y equals 40 times 1/3 to the x. You have a little bit of additional practice today, and then a mastery check, and then you're done for the day.